Good morning. Welcome to our session on AWS IoT events. This is a new service which was just launched Monday evening. I'm Sahil Kumar. I'm a senior manager with AWS IoT. And with me, we've got two partners today. We've got Tolga Tarhan. He is a CTO with Autica. And then we've got Ram Shastri Chaudhary. He is the global head of IoT consulting for TCS, or Tata Consultancy. Before we get into the session, I just want to talk about what we are covering today. We're going to talk about why is it complex to detect critical operational events at scale and respond to them. That's really what the service does. We're going to talk about how IoT events solves this problem. Then we're going to talk about how it really works, and we're going to talk about how to get started with it. We're also going to talk about IoT events as a building block, so our customers and partners can build custom systems, mobile applications, et cetera, on top of IoT events. And then we have two partners here, Autica and TCS, that will be the more interesting part of the presentation. They're both going to do demos. Autica is already using IoT events. They're going to do a demo showing tracking rental scooters as an example. So we've got a little scooter here, and we're going to kind of move it around on stage and show you how it tracks events. And then TCS is going to talk about wind turbine fault detection and response. Obviously, we don't have a wind turbine here on stage, but we'll kind of show you on the browser. So what are operational events in this context? There are several things which we consider operational events for the purpose of IoT events. One is equipment malfunction. So that could be like a motor being stuck, commercial refrigerator door not opening, something like that. It could be any sign of poor quality, so a sign that quality is not where you need it to be. It could be a sign of wear and tear on equipment requiring preemptive maintenance, or a part change, like changing a dirty filter or a battery which is depleting in charge or something like that. It is also the state of processes. So this is not just for equipment, it also could be applied to processes. So it also helps to determine the state of processes as determined with a combination of discrete inputs and ML models. And we'll talk about that a little later on, how you can use ML for probabilistic state determination. So what problems are customers trying to solve? And we've kind of put that into two categories here. The first category is what we're calling predict, prevent, and diagnose. And here we're going to talk about three things. The first is predictive maintenance, which usually starts with simple rule-based alerts until sufficient data is collected. And then ML models can be applied to do more predictive detect complex behavior patterns and anomalies and stuff like that. The second is predictive quality. So using near real-time anomaly detection and predictive analytics, we can detect quality issues at their source. So if we could detect intermittent failures in an airplane or an assembly line of some kind, or even like a soda dispensing machine in a restaurant, we can send a technician with the right parts to fix that problem before it really becomes a problem and it breaks down, and that saves valuable time. And the last one is accurate failure diagnosis. And this is all about reducing false alarms. So there are a lot of detection systems out there today, and they're mostly just get turned off or the alerts get ignored because of the high rate of false alarms. So if we can actually reduce the false alarms, then these alerts can get the attention they need. So that's kind of another use case of this. The second category is improving efficiency. So here we talk about improving efficiency of equipment, processes, products, staff, anything, right? In an industrial setting or a manufacturing setting or a commercial building or a service industry, even small improvements can save millions of dollars in savings. And uncovering early causes of disruption can significantly reduce planned downtime, and that increases throughput. So the cost of having an assembly line down for a single minute, or an airplane sitting on the tarmac, or in the case of that soda dispensing machine, it not working and people not being able to pour drinks, even those small improvements can translate into big savings at scale, and that's kind of what this service is there to solve. So where are we today? Industrial enterprises are adopting IoT at a fast rate to monitor operations, increase the quality of plants, plant safety and reliability, and then even consumer electronic OEMs are adopting IoT at a fast rate to offer new consumer experiences and improve the efficiency of their equipment and processes. And at scale, these IoT deployments consist of hundreds of thousands of sensors, depending on what you're dealing with, and lots of management applications. And for these customers, it is hard to detect a complex event, such as when the equipment variability will reduce the quality of output. So what today customers are doing is they're first making homegrown applications to collect diverse sensor data, and then they are combining that with the right decision logic to trigger yet another set of applications to apply actions. And IoT Events does this all together in one system. So the current systems are complex, they're error-prone, they're hard to get right. So what I want you to think of is an example of a cargo handling machine for a shipping company, right? A shipping company which is handling cargo handling machinery, it's handling and doing management software for ships, ports, terminals, and local distribution. Ocean ports these days have become smart, like a lot of other equipment out there. Millions of shipping containers have environmental sensors and digital IDs and local location trackers, and each yard crane can have tens of thousands of sensors. That being said, port software is really old, right? It was built to manage paper and manual labor processes, and supplementing that with digital information today and the new software of today often fails to scale. And that's what a lot of customers have tried, and it doesn't scale. So it's hard. Homegrown applications are generally inflexible. They do require complex recoding. They're hard to manage. Most of them are on industrial PCs, on-premise equipment. So this means customers need to build applications, and the applications they usually end up building are for simple events. They don't update them often, and they miss the critical events, which require combining diverse sensor data to get a complete picture of the operation. So the question we're posing is, how can your business benefit from detecting complex events at scale and triggering real-time action in response to those events? And here is where the new service, AWS IoT Events, comes into play. So AWS IoT Events is a new cloud service that continuously monitors data from equipment and applications for changes in operations and triggers appropriate response. The service is intended to help enterprises understand the condition of equipment when it takes more than a single sensor to get full context in order to reduce cost of maintenance, discover new insights, and automate operations faster. So if you look at the picture on the screens, there are inputs on the left. They get routed into what we call the complex event processing engine, or the state machine. And that's where, based on the inputs, we are managing the state of the equipment or the process. And as those inputs come in, based on the logic you've provided, the equipment or the process moves from state to state, and those changes in state could trigger actions, right, if you've configured them. And there are several types of actions possible. We'll get into that later. So the key benefits are monitoring multiple sensors and applications simultaneously to detect critical events. Results from our service, which was launched earlier this year, IoT Analytics, can also be used as an input. And here's where the machine learning aspects start kicking in, because you can take analytics, you can run an analytics query and take the output of that analytics query as an input into IoT Events. The service is both idempotent and it's strictly consistent. It manages state of devices and processes, and it's instantly scalable. So let me talk a little bit about that. So that's really useful for consumer electronic OEMs, right? You could have hundreds of thousands of devices. You don't need to write any code. As new devices come online, it'll immediately detect input and scale. I'll talk a little bit about how it does that later. And then there's an action library of pre-built responses, which includes integration with AWS Lambda, so you could trigger any external system as well. You don't have to necessarily be triggering AWS systems. So back to our port automation example, building a new solution using AWS IoT Events, our customers are looking at re-architecting port automation software. And what they're doing is trying to remove those event scripts that they have today to make the system more scalable, more flexible, and easier for port managers to configure. Customers can pre-build event detectors for their port automation software across equipment and common container types, and then allow the individual port managers at individual ports to assign appropriate actions based on their individual port operations. And as a result, port managers can more quickly detect things like when a container has offloaded and is ready for the next job, and that can shave minutes off each container move. And then here's a statistic where increasing US port efficiency by even 0.5% results in an additional $263 million a day in freight value. So that's a lot of money that can be saved by just improving how we automate our ports. So how does the service work? AWS IoT Events takes inputs from multiple sources. It takes device data from IoT Core. It takes results of analytics from AWS IoT Analytics, and it takes input data from a Greengrass device running on the edge. It can also take any external input via a PUT API. And that's really how you route anything which is coming from outside AWS into IoT events. Your inputs are not necessarily coming from the AWS services. These inputs then get routed to an event detector. The event detector is a custom authored JSON that models a piece of equipment or a process as being in one of several states. And it detects one or more types of events using the multiple signals that are going into the detector. And then you can apply logic, Boolean logic, or any other kinds of mathematical functions to that. When the detector detects an event, it triggers actions. And that action may result in a change of state as well. What are the different types of actions possible? So there's an action library, and we trigger actions within seconds. Common actions are sending a message via AWS SNS, triggering a function in AWS Lambda, which obviously can trigger external applications as well. You can write a record to DynamoDB, or you could send a message to a device using IoT Core. So there's lots of different types of actions that are possible, and more will be coming later at GA. IoT Events truly brings a lot of our recently launched services in IoT together. So I'm going to talk a little bit about how it integrates with all these other services. So AWS Greengrass provides an easy option to send inputs from edge devices running Greengrass to IoT events without the need for additional formatting. So it makes it very easy to get inputs from Greengrass. IoT Core provides an easy option for sending messages from devices directly to IoT events, and IoT events can also publish messages back to devices, so there's bi-directional communication there in an easy way. With IoT Core, you of course get to use, for those of you who've used IoT Core, you must be familiar with things like Message Broker and Rules Engine and Device Shadow, and you get to interact with that as well if you are interacting with IoT Core. So for example, you could send a message to a device that is offline using its shadow, right? So you could send an action to the shadow. IoT Analytics also provides an easy input to input analytics queries directly into IoT events. The next slide will kind of talk a little bit more about that. And then we have a newly launched service. There's a session going on just right now about it as well. That's IoT Sitewise. This is a service for industrial customers specifically. And what the service does, it moves the large volumes of industrial data that is sitting today in factory historians or OPC UA servers on-premise. It moves that data to the cloud, and then it allows customers to model their equipment and their assets in the cloud, add context to what that data is associated with, and then calculate metrics like OEE and efficiency and performance. And those metrics can then be used for building dashboards and views and mobile applications and custom systems, whatever you want. Those metrics can also be taken as inputs into IoT events. So that's another way IoT events kind of brings all these solutions together. Again, IoT Sitewise, it was just launched this week. You can find out more about it online, or there'll be a session on YouTube posted as well. So integration with IoT analytics. So integration with IoT analytics enables the use of ML to identify behavior patterns that can't be detected with the simple if-then-else logic or Boolean logic. IoT Analytics integrates with AWS SageMaker to provide ML in event detection and probabilistic state determination. It also integrates with Jupyter Notebooks, so you can actually schedule your custom analytics to run every few minutes, and that'll kind of run automatically, and then those outputs can go as inputs into IoT events. So IoT Events takes output from analytics, combines it with other telemetry data that might be coming in from other sources to detect events and then take action. We talked about this earlier, so we easily scale to millions of devices. How this works is when you're connecting homogeneous devices, so let's say it's an Echo or a smart TV or a smart robotic vacuum or any kind of other kind of consumer electronic device, OEM might want to have one or more detectors per device. So they only have to configure the detector model once for that particular type of device. As new signals from those devices get detected, it usually will be associated with something like a unique device ID or a serial number. IoT events will automatically detect that, and it will spin off a detector for that device. So as devices get sold, they come online, people connect them, these detectors just automatically keep spinning up. And that's a huge benefit for OEMs because they don't have to really do any coding as these new devices come online. And lastly, IoT events can be used as a building block by our customers and partners. So it does have a console. I'll talk a little bit later about that. But it is also completely driven by APIs. So APIs can be used to monitor and author event detectors. They can be used to programmatically extend the input library, so it's not just limited to the inputs I talked about. And you can also extend the action library, so it's not limited to the actions I already talked about. It is a fully managed service. It provides an elasticless, serverless experience, so there's no hosts, there's no sharding, there's no resource provisioning. It automatically fully scales, and this really allows partners, as you're going to hear from 2 partners now, to build custom systems and mobile applications. So Onica, who is going to come up here next, has taken advantage of this capability, and in a matter of no time, they have built custom applications on top of IoT events with very little coding. So I'd like to call Tolga on stage, and he will take you through their use of IoT events.
Turn that on. All right. Yeah, cool. Hey guys, my name is Tolga. So Onica is an AWS Premier Partner, and we help customers be the best cloud consumers that they can be. And we do this in a number of ways, from migrations to big data to AI and serverless. But today, let's talk about IoT. What we found is that every IoT use case has the same few problems on day one. For example, on the hardware side, you need to deal with connecting to the cloud via cellular or Wi-Fi. You need to deal with power and batteries, which are actually very complicated to do safely. You need to deal with, on the software side, ingestion, storage, building robust APIs that are then powering the experiences that you're building with your IoT app. So after doing this a bunch of times and realizing that we're doing the same thing over and over, we decided to build a reference architecture. And what I'll talk about today is how that reference architecture and IoT events came together. And I promised my marketing team I would actually ride this scooter on stage, so we're going to give that a shot. The reference architecture has kind of hardware and infrastructure and software components. On the hardware side, we took an ESP32, a really common processor, which has Bluetooth and Wi-Fi built in. And we added all the supporting circuitry for stuff like power and all that nice stuff. The reference design is meant to start your prototype on day one and just build something with hot glue and cables, which is literally what we did here, and then mature that design and grow with you into the production design you're going to actually use and be a custom finished design. So we're not a hardware vendor. What we're trying to do instead is sort of bootstrap the design process. And then on the software and infrastructure side, imagine that same sort of concept for those bits and pieces. So today we're going to talk about tracking scooters. You've seen these scooters if you live in a big city. They're littered on the sidewalks of Los Angeles. And you go up with a mobile app, and you unlock the scooter, and then you can ride it. It's electric. And you get where you're going, and you end your rental on the mobile app, and they charge you a few dollars for the ride. So we took our IoTanium reference platform. We added, in fact, I think I have a slide. There we go. We added a GPS. We added a motion processing unit also to figure out gyroscope and acceleration and all that. And we wrote about 40 lines of code on the device. And that gave us our connected scooter. And we did it hardware-wise in about a day. So on the scooter, and I didn't bring an electric scooter with me. I thought that would be challenging, so I just have a razor here. But on the scooter is a box, and the box is quite a bit larger than it needs to be, just so we can see it and play with it and touch it. But it basically looks like that, and you can see here the colors representing the components. So the blue box is IoTanium, the red box is the GPS, and the yellow box is the motion processing unit. And literally, cables and those things are held down by glue. So architecturally speaking, this is really, really simple. And if you're paying close attention, realize there's no code in the cloud in this design. So we have our scooter, off to the left, we have IoT Core topic, where we're publishing raw data, just XYZ values for the accelerometer and gyroscope. We then pipe that data into IoT Events, and IoT Events tells us, is the scooter moving? Is the scooter stopped? Is the scooter possibly stolen, right? And then it feeds the resulting state information back into IoT Core, where we pick it up in a web UI. I'm going to show you that web UI in just a sec. The state machine looks like this. So the state machine starts in the ready state. The scooter is parked. It's locked. If you go towards the right, then you can be rented and stopped, right? So the rental has begun, but you're not moving. You can be rented and in motion, or you can be rented and maybe abandoned, right? So the rental started, you started riding the scooter, and then it hasn't moved for a while. So we wonder, did the user forget to end their rental and they just walk away from their scooter? On the other hand, if we're not rented, we could be stolen. We could be moving when we're not rented, which is a bad situation when you're in the business of renting scooters, right? So this whole state machine is managed by IoT Events. We didn't write any code to manage it at all. So I'm gonna do this live demo here, and we're going to all hopefully see this work. Make sure this is on. Cool. All right. So I'm going to turn on my scooter. Just give it a sec to get turned on. So this is a Razor, pretty basic scooter. And hopefully she's going to behave for me now. Come on, scooter. All right. Oops. There we go. OK. So I'm going to switch to the I thought I was switching. There we go. Cool. All right. So I'm going to explain what's going on here in a second. So this scooter is currently not moving. And it was moving as I was messing around with it. So it thinks it's maybe stolen at the moment. See the timer there on the right counting up? When that timer gets to 10. All right. We've stopped moving. We no longer think we're stolen, right? Now, I should have thought about this. If I start moving, we get into this theft suspected state, and we wonder, hey, maybe we're being stolen. We're not sure yet. But if we stop moving pretty quickly, we'll go back to the locked state. If I start my rental now, so in the mobile app, let's say that I just rented the scooter. Now I can start moving, and you can see our little scooter moving on the screen. And the scooter can stop, and when it stops, we'll detect that and show that we're not moving, if I can hold it still enough. Or, maybe we won't. But it's because I'm not actually holding it still enough on stage, which is really cool. You guys can see the accelerometer values at the bottom there. On the other hand, if I continue to move it, you'll notice the continued movement happening. And, oops. There we go. All right. And if I stop my rental, you'll see it actually end the rental, and we'll be able to move on and go back to sort of the locked state. So the connected scooter in this case is using the Wi-Fi that's on my desk here, and that's part of our challenge today. But you get the idea of how we built this entire sort of correlation engine around just IoT events. So I'm going to actually show you guys what this looks like when there aren't any Wi-Fi challenges. Because intelligently, we did actually make a video. So I'll show you what would normally happen. So this was recorded in the hallway, actually, just before the demo. So you can see here, the scooter's not moving, starts moving, then we'll stop moving. And now we're wondering, or we'll stop moving again, and then in a second we're gonna stop moving for a period of time and see it do that abandoned workflow that we talked about. So hey, we're not moving. It's been 5 seconds of not moving. You can see the counter on the lower right. We get to 10 seconds, and we've been abandoned, right? And so if we start moving while we're abandoned, then we're like, all right, well, maybe that was a false alarm. Everything's OK. And then you can see here again, about 6 seconds of non-movement currently in the lower right, the timer. We're going to get to 10, start wondering if we're abandoned. And when this goes to 10, you'll see that we're actually going to go ahead and just assume we are done and lock the scooter again. And then if it moves while locked, there's the theft suspected. If it stops moving, we're back. Right? So that's the workflow. And my scooter here, I'm going to just move it off the side. OK. So, and you can see it's detecting. So now it's, the Wi-Fi is working, and we're having good luck, but such as it is. There we go. All right. I lost my clicker. So what did that look like on the code side? This is what the firmware looks like. This is one of 2 slides of firmware. We basically connect to IoT Core. We read 1 second worth of data from these sensors, aggregate that up, and we transmit raw sensor data. Here's what that read routine looks like. You can see we're just, for the time period that we want, which is 1 second, getting the maximum value of the accelerometer and the gyroscope and saying, hey, that's the movement that was or was not detected. On the cloud side, this is what that JSON definition looks like. So you can see here one particular event that we're capturing. So this is the non-movement while we're stopped event. So the scooter is not moving, and it continues to not move. And this is counting up this timer to see how long have we been not moving. The most interesting takeaway from this whole thing is that we built an entire application with no servers, no infrastructure, and no code. So there's a web application, there's some device firmware, but there's nothing sort of running in AWS except for that definition of our state machine. So that's what we did. We've done this just in the last couple of weeks with the IoT events team. It's been a really fun adventure. And with that, get back to you.
All right, so let's really quickly talk about what were the benefits here with IoT events. So as the Onica demonstration showed us, IoT events helps our customers and partners by being able to quickly detect critical operational events when Wi-Fi is working, yes, manage the state of equipment and processes, easily integrate with existing solutions. So in the case of Onica, it was their IoTanium hardware, and we quickly integrated with that. And then be up and running with demonstratable results in a matter of a few days. They did this very quickly. This was literally done in the last few days. So one of the features of this service, which you didn't see, which I talked about earlier in this demonstration, but you'll see in the TCS example, is the hundreds of simultaneous inputs, right? So this only had a few inputs because it's the movement of the scooter, but in the next example, you're going to see a lot more inputs and how that kind of interacts in the wind turbine example. So how would you really go about modeling a detector? So what you see here on the screen is, I'm just going to walk through a simple example of a package conveyor belt where we want to detect and action lost packages on a package conveyor belt. So on the left, you see multiple inputs going in. In the middle, you see we've kind of modeled a state machine. What we're doing here is creating a detector that defines a conveyor belt as being in one of 3 states. There's a belt empty state, a belt loaded state, and a package lost state. Then we create events that move the detector from one state to another. So such as the package fell off event will move the detector from the belt loaded to the package lost state. Events are defined here using Boolean logic and that evaluate multiple signals. So for simplicity, we're just doing a few signals here. So the package fell off event is defined as status being loaded and weight being 0 and the proximity end being 0, indicating that the belt is in a loaded state, but there's no package weight that's being detected, and neither has the package exited the belt. And then here, the system automatically and immediately responds to an event by triggering an action. And here, the action shown is an SNS notification to notify maintenance to come and recover the fallen package. So how do you set it up to work? And here we've got some screenshots from our console. Of course, it's completely API-driven, but there is a very rich console that comes with it too. So before I get to that, there's some terms to remember. So there's inputs, which are incoming messages or signals. There's a detector model, which is really the definition of your detector, which is what we saw in the previous slide. And then there's a detector, which is a single instance or occurrence of a detector. And that's what comes into play when you have multiple devices of the same kind, right? And that's based on a unique ID, like a serial number. So to configure, you define your inputs into IoT events. Then you create a detector model to define the events you want to detect and the actions you want to take. Then you deploy to production, and the system basically automatically spins off detectors dynamically as inputs are detected. There is a visual programming layer in the console. You will see this with some of our newly launched IoT services. They have a very similar console where you can do drag and drop, you can add states, then you can connect states and add transitions between them, and those become events, and then some events can be associated with actions. So you can visually draw this, and then it'll create the JSON in the back end for it as well. Actions. So we trigger actions in multiple systems. I named some of these before, but we'll just go over this quickly again. We have the Amazon Simple Notification Service, or SNS. That is for email notifications, mobile alerts, SMS, whatever. Actions in IoT Core, so that's sending a message to a device via IoT Core. Any external application can be triggered via Lambda. And when we go GA next year, we're going to have actually a full action library with several more pre-canned actions you can easily select and take. But right now, you have the option of adding those if you want with Lambda. The actions library is also extendable with DIY solutions. So some features of the service that I want to highlight before we go to the TCS part of the demonstration. The service is idempotent and consistent. It processes messages in order and ensures that state integrity is maintained across failures. So it's that maintaining state is a huge part of the service, and we really make sure that state integrity is retained. It ensures high availability, but it does prioritize consistency over availability. It is strongly consistent in processing messages and in reporting, and it processes messages and initiates action in near real time. Lastly, there's a feature, you kind of saw it in the Aunica demonstration, at least one of these, and that's timers and variables. So what are timers? Timers can be used within detectors to detect time-based events, such as a timeout or a heartbeat. So how many seconds since a certain signal is received? In the case of the Aunica demonstration, it was how many seconds since the movement, right? And then there's variables, which you can use within detectors to count events of interest. So it's like a counter. So you can track what happened in the past. So every time X happens, you increment the counter by 1, and when the counter reaches a certain threshold, you can trigger an action. So things like that. So you can kind of store and remember what happened in the past. And so with that, I would like to call on stage Ram. He is the global head of IoT consulting for TCS, and he's going to talk about their use of IoT events. So Ram.
So which is up here, okay.
If you want to switch, you'll go to HDMI too.
Yeah, but which is the presentation?
Yeah. Presentation's over there.
Oh, okay. Hi, everyone. Just to reiterate, my name is Ram, and I manage a group of consultants for TCS, and we advise our clients on various IoT problems that they have end-to-end in all verticals, bringing to forth TCS solutions as well, those of our partners like AWS. Just very quickly, I want to get right to the chase, but just to give you, at the core, everybody here in this room probably knows that IoT is the key enabler of digital transformation, or what we call digital reimagination. And how do we do it? Through IoT, through connected products, connected assets, so on and so forth, and enabled through, at the core, of course, IoT is real-time information, gathering real-time information from various assets, analytics, so on and so forth, and a closed-loop feedback. One of the things that Sahil spoke about was the ability of IoT events to generate an action through the IoT core to send back feedback. So that's the feedback, closing the feedback loop. And of course, integration with back-end processes. That's what enables the transformation, the digital transformation. What I'm going to talk about is a very important problem. At the outset, let me mention that our partnership with AWS is a very fruitful, as we say, a digital twin in IoT parlance. In that, one of our key strengths is engineering and domain knowledge. All of you attended the CEO speech yesterday, where he made a big pitch about how analytics is so easy to use. You have the platform support, hyperparameter tuning, so on and so forth. But one element that is still required is the ability to bring in very sophisticated engineering domain knowledge. And that's what is this partnership all about. So in this case, you're seeing the global push for renewable energy penetration. And wind energy is a key element of that. Now, what's one of the key challenges of wind energy is that it is intermittent. I mean, you don't get wind whenever you want. It's subject to the whims and fancies of nature. So, but as an engineer, as a engineering system, you have to be ready to tap into that wind when it is available. So, if you have a wind farm, ensuring that the turbine operates with maximum efficiency all the time is essential, because when wind is there, you want to capture it. Because if you don't have wind and the turbine is not functioning, it's kind of a double whammy, right? So that's the key. So the problem statement is essentially, you have these wind farms installed. Now, wind is a very complex engineering system. It consists of a generator, rotor, shaft, gearbox, braking assembly, and you can imagine, again, to quote Sahil's point, this generates a tremendous amount of data. That's for one turbine, but you can imagine in a wind farm and then globally. So we're working with a particular client to help monitor these wind turbines, generate these real-time data, and then use the IoT event to do this complex event processing. So now, here is the key. In a simple situation, you could have, if the temperature, if the gearbox parameter, some parameter exceeds the limit, then issue an alert. But that's not good enough. I mean, that's where the engineering knowledge comes in, along with the complex event processing, to be able to dive through and get to the root cause of why something happened. You may get an alert, but that alert may not be something at the gearbox. It might be because of something somewhere else. That's the problem that we are using. That's why we are using these IoT events. So basically, that's what this problem statement is to do diagnostics and identify cause of failure. And of course, for obvious reasons, as I explained earlier, downtime, has a huge impact. So this is the remote monitoring solution. So the challenge is it requires alerts to be based on multiple events, based on multiple signals, times, and conditions. So I just described what a complex system a turbine is. Now the alerts, what we are doing here, I must admit that in this particular demo, we're still using complex event processing. In other words, I'm not talking about predictive or condition-based maintenance or very sophisticated machine learning just yet. But we are still using engineering models in the IoT events to be able to generate these alerts and then link one condition with another, as you'll see in the next slides. And of course, the visualization of parameters and trends. And then that arrow there to the right is important. It's hundreds of parameters is what we are capturing. Now, when you see the demo, you will see this, but here is the the state machine, or if you will, the tree that we are building up through the IoT events. So you have a turbine malfunction. Now you might think that the problem might be due to, you see, the increased CW pump or motor ampere current or pump head, but that need not. See, that will be the naive way of looking at it. I get an event, something happened to the turbine, so maybe I look at those events. But no, you got to dig further down the tree. You see, there are three possible causes of that: a mechanical damage, flow area increase, or flow area bypass. Now, that again may not be because of the decrease in the pressure ratio or turbine efficiency or upstream pressure. You got to dig still further down, and then you'll come to the real cause of the event, the problem, and that's a gland C leakage occurring due to one of the two parameters there, the leak flow offset, the leak offset flow, or a temperature increase. So you get the drift. So I might get an alert. So the naive way of doing an IoT, if I were to just build, all of us have fun building with a Raspberry Pi, an IoT application where you just get a temperature, you go into the IoT core, and you generate an event if something exceeds a threshold. But this goes much deeper and builds up this entire tree through that complex event architecture that Sahil showed. Now here is the rough architecture. You see the turbine there. I won't go a lot of details. There's a lot of engineering on the left side. Typically, all of the sensor data from a turbine or any industrial machine, for that matter, is controlled. I mean, an industrial machine like a turbine is controlled by a PLC, which stands for Programmable Logic Controller. That then sends all the data is connected to what's called an OPC. It's an industrial protocol. And from there, that's connected to the AWS Greengrass, from where you use the MQTT through the AWS IoT and then IoT core. And from there, based on a simple rules to send events to different places, it enters into the IoT events, where we have our engineering models coded with very limited coding, but using the capability of the IoT events to do this complex event processing. And from there, once essentially what we are doing in that IoT events is building up the tree that I showed you in the previous slide. And from there, using the Amazon SNS, we send a simple notification. And in this case, that web UX is subscribed to that SNS, and you start getting the visualization and the trends and the alarms and so on and so forth. Okay? So with that, so you'll see in my demo now, what you're going to see is this particular tree being built up. You'll see initially everything is hunky-dory. Everything is green. What that green indicates that everything is within their limits. Slowly, you'll see that some of the boxes will change to amber. That means that a first level threshold is crossed. And then you'll see quickly it will turn into red, which means now we have entered into a critical state. But at the top, the turbine itself loss entering into a critical state does not mean that it is due to, as I said, that motor ampere current, the current or the pump head. But you'll have to dig right through below, and then you'll see that the reason for the outage is that gland C leakage. So with that, let me go into command. Yeah, so we have to go to HM. I did. Yeah. Yeah, so please observe this. The bottom portion you'll see as, yeah. So you see, just observe the gland C leakage, and you'll see as the demo is progressing, as the data is coming in. By the way, all of this is happening in the AWS, in the IoT events. Now you'll see very quickly that there are two thresholds. You see that one and then the red dotted line below. You'll see as that guy crosses that, hopefully there you go. You see that? That's the first level threshold. Now that has resulted in an amber. And then as it further goes down, you'll see that it enters into a critical stage. And there you go. So you see, the actual event is that gland C leakage, but then that has petered up all the way up to a loss of the turbine. Now, I won't show you the rest of the user interface, but actually you'll see an alert that in the user interface, that it is the turbine that there was an event generated when the turbine loss occurred, and it will let you dig through all the way, and you'll find that the reason for the loss is this last seal leakage. So that's basically the demo. So what's happening is, again, just to reiterate, all of this data is coming in, all the real-time data that I just alluded to earlier. It's coming in through the AWS IoT core into the IoT events, where we use engineering models based on all the turbine engineering mathematical models of the turbine to determine this, to build up this tree through whatever tools that AWS events gives us, IoT events gives us, and generate this visualization and help you with this root cause. With that, so we go back to this one, right? Yeah. Yeah. So in summary, what is IoT events helping us do? It's helping us in root cause analysis of wind turbine. Now again, if you go back, if you didn't have this capability, if you recall, either you have to do this manually, or, as I mentioned earlier, you do a naive way of where you get events, and then if you look at simple thresholding, that doesn't let you do this root cause analysis that I just described, of going from the top level of the tree all the way to the bottom. This helps you do that. So hundreds of sensors, as I said, multiple simultaneous input changes. Now that second bullet is very important. Now, minimum coding required in the sense of setting up all the infrastructure. There's still the engineering logic that we need to program. That is very important. But in terms of the platform support in building up that state machine, in building up that tree, and that's exactly the third point. It helps us worry about the business logic. Because as I said, in many of these industrial machines, that part about knowing the intimate knowledge of the engineering process involved is key, no matter if you don't mind me saying how intelligent a deep neural network might be. But still, you need this this engineering knowledge to be built in, and that's what we bring in. So with that, I will close, and I think I'm 2 minutes. I give you 2 minutes.
All right, so we'd like to summarize now and then tell you how to get started. IoT events is basically a complex event detection and response system, monitoring multiple inputs, triggering responses. It's idempotent, strictly consistent. It's essentially a state management system at heart, so it's managing states of devices and processes. It's instantly scalable, and it can trigger almost any actions via Lambda. The service is, at its core, intended to help enterprises understand the state of equipment when it takes more than a single sensor to get the full context of what is going on in order to reduce cost of maintenance, gain new insights, and operate operations faster. So how do you get started? IoT Events is released now in limited preview mode. It is in 3 regions, US East 1, US West 2, and EU West 1, so it is in Europe. There's a link on the screen. You can go there to learn more. During the preview phase, there is no billing. It does, however, require whitelisting, so you need to kind of register for it, and we need to approve that, and you get whitelisted in a few days. It should not be used for production workloads yet, because it's not GA. It will be GA sometime next year. Our standard terms of usage apply, and we absolutely want your feedback. So please register, try it out, and give us your feedback so we can make it better. Thank you. There is a session survey in the mobile app. We're going to be down here taking questions. There's some people from the team here who can help answer that even in more detail. So thank you for attending.